In this video, we're going to discuss acid and base chemistry. So acids and bases, there's a lot of definitions for them depending on how complex you want to get with the chemistry, but we're going to work with some of the earlier and simpler definitions. So we're talking about Arrhenius acids and bases and Bronsted acids and bases. And for our purposes, an acid is a compound that releases H+. A base consumes H+. How this actually looks, if we have something like hydrochloric acid, well, it reacts and creates H+ and Cl-. Really what happens is that we bubble HCl gas into water and we create aqueous H+ and aqueous Cl-. In this case, HCl is our acid. It was the molecule that gave away H+. And so H+ is our proton, or it is our hydronium. There's a lot of names for it, but it is what we are releasing when the acid releases. Well, a base is something that consumes the H+. So if you have something like sodium hydroxide, well, really in solution, this is a sodium and a hydroxide. And if they run into an H+ aqueous, it makes water. And the sodium is actually still there. It didn't do anything. In fact, we wouldn't consider it part of this reaction. It was a spectator ion. But we had to get the hydroxide into solution somehow. Hydroxide is a base. It will consume that H+. Other things that can do that, ammonia. And ammonia plus an H+ will become ammonium. This is where we get the polyatomic cation. Both of these are bases because they consume H+ in solution. Our hydrochloric acid is an acid because it releases H+ as part of its reaction. So these are working definitions for acids and bases. Well, acids and bases are just a subtype of reactions, like oxidation or displacements or burning or anything else. Acid-base chemistry are just ones that involve protons. But that's extremely common. Earth is filled with water, life is based on water, and water has a lot of protons in it. And so this becomes very relevant for a lot of chemistry that humans will undertake. Well, because we do everything in water, there's also a very important reaction where water plus water can react with each other. Remember that water is HOH, and you have another O with two H's. If one of these just happens to hit the other just right and hard enough and bounces off, it can actually steal that hydrogen. The net result of this is that you actually end up with OH- and OH3+. The two waters can swap and pass off one of the protons, one of those hydrogen atoms, except it leaves as a proton as charged, and so one of them ends up with a negative, one of them ends up with a positive. We often write this as just water can break apart into H+ and OH-. H+ and H3O+, if it's aqueous, they're actually the same thing. That proton is surrounded by waters and it actually just sticks to one of them. But it's often more complicated to track that extra water than it is to just talk about the hydrogen plus ion. And so more often than not, we simply refer to it as H+ instead of H3O+. Truth is, they're identical in an aqueous solution. But water is doing this all the time, which means in a bucket of pure water, you have a little bit of H+ floating around and a little bit of OH- floating around. They're in equilibrium. It's always doing this. There's not a lot. In fact, at room temp, there is 1 times 10 to the negative 7 molar H plus. So 0 point and then 6 zeros and a 1. There's not a lot. There's 1/10 millionth of a mole in a liter of water. But we can change that. As we add chemicals that free up more H pluses or consume them, we will change that amount. We need a way to talk about it, however, because since there's such a small molarity to start with, if you change it by 100 times, you throw off that equilibrium and increase it, it's still a small number. But you could alter it by 10,000 times, 10 million times. There's a lot of ability to change when you have a number that small. It's easy to multiply it. As a result, we can't really just talk about the molarity of H plus most of the time. Instead, we talk about the pH. If you've ever had to test some water supplies, a hot tub or pool or anything like that, pH is what we tend to measure for. We want to know what the pH of a solution is. What is pH? It's really a measure of the molarity. It's the negative log of the concentration of H plus. And so those brackets, remember, represent molarity. Our pH is just the negative log. Lowercase p is an old symbol for logs. We don't tend to use them as much anymore since calculators became a thing. We can just do the raw calculations easier. But they're still used in reference for acids and bases. What does this mean? Well, I can just plug in my concentration. I have a pH. It'll equal the negative log of 1 times 10 to the negative 7. If you actually plug that into your calculator, you will find that the pH is just 7. How would we find that normally? This is occasionally because we haven't used logs often for a very long time. Let's review log real quick. If you ever have something where you want to find the pH and you know the concentration, well, you can just plug the concentration in to your calculator. Negative log of concentration will give you pH. But what if you were told the pH? How would you find the H plus concentration? Well, to get rid of that log, to manipulate the equation so we just have H plus on its own, the first thing we have to do is multiply by -1 on both sides. This will move the negative. You'll get negative pH is log of H plus. This is important because now we can get rid of the log. Logs are an interesting use for anti-exponents, where 10 to the first tells you to multiply by 10. A log is actually saying, hey, what number would that exponent be? Instead of finding the big number, it asks about the exponent part. And so we need to get rid of that log. And how we do that? Well, it's the counterpoint to the power of 10. If you turn both sides of those into the exponent of 10, you end up with 10 to the negative pH. Well, 10 and log are opposite commands. They cancel. And so if you ever have the pH and you want to know the concentration, it simplifies out to this. 10 to the negative pH is my H plus. And if I know my H plus, the negative log gives me my pH. So here's how we can manipulate them. What it's really useful for, though, is looking at our water supply. Neutral water, pure water, we said had a pH of 7. As you go down towards 0, or up towards 14, what's happening is you're just changing the molarity of your H+. Put a different value in, you'll get a different pH back out. Well, as your molarity gets bigger, you actually get a smaller pH value. Go ahead and run it if you want, but negative log of 1 times 10 to the minus 6 is going to equal 6, versus our original negative log of 1 times 10 to the minus 7, which we said was pure water, which equaled 7. Well, 10 to the minus 6 versus 10 to the minus 7, 10 to the minus 6 is bigger. It's less negative. You divide by 10 less times. So we're actually more acidic when we're a lower pH. And if you make 10 to the power greater, so let's say you had negative log of 1 times 10 to the minus 12. That is a much smaller molarity than our 10 to the minus 6 or 10 to the minus 7, but your pH is going to calculate out at 12. So the lower your molarity, the bigger the pH value is going to be. Well, if we have less H plus around, we say that it is a more basic solution. If we have more H plus around, we say it is an acidic solution. And so our pH is good for telling us what's the situation with this liquid. Is it acidic? Is it basic? How acidic and how basic? And so pH is what we'll use to reference the acidity of a solution. Molarities will come up often, but we'll convert it to pH for easier reference, because the very large difference in molarities doesn't look quite as daunting when you're only going between 0 and 14 for a pH scale.